Well, so my pleasure to introduce Elena Berardini from Telecom Paris, Institut Polytechnique de Paris, France. And she will speak about Riemann-Roch spaces and algebraic geometry codes. Please.
Well, okay, thank you very much for the introduction. And it is a pleasure for me to be here and to talk about my work to you. So I really would like to thank all the people that were involved in this conference. So thank you very much for letting me be here. And so my talk will be focuses on Riemann-Roch spaces and the important role that they play in coding theory and in particular in the construction of some codes, which are called AG codes. And I will talk about these spaces from two different points of view. So I will talk about Riemann-Roch spaces of curves, first of all, and so about how we can effectively compute these spaces, and so how we can then compute AG codes from curves. And then I will be focused on Riemann-Roch spaces of surfaces, and so how can we use these spaces and some tools from geometry in order to study AG codes from surfaces. And so first of all, let me tell you what is an error correcting code. So it is a tool that allows you to transmit and store data, which has the feature that you can detect and correct the error that can occur during this transmission. But from a mathematical point of view, we will more be interested in what are called linear codes, that are FQ vector subspace of FQ to the n, where FQ is the final fields with Q elements. And to those codes, we can attach in general three parameters that are the length of the code. So you can imagine a code word as a vector in the code, and so the length is nothing but the number of coordinates of the vector, the dimension of the code, which is this dimension as a vector subspace, and the minimum distance of the code, which is basically the number of non-zero coordinates of every code word, and then you take the minimum of this number. And K and D are linked to the capacity of transmission and of correction and detection of the code. And those codes turn out to be useful in several applications. For instance, they were used in the 80s to construct the first compact disc. They were used in space communication by the NASA. You can find them in QR codes. They are also used nowadays in the clouds and in post-quantum cryptography. And of course, as you can imagine, one of the main goals is to have codes that allows you to encode as much data as possible and to correct as many errors as possible, which from a mathematical point of view can be said by saying that we want code with K and D as big as possible, knowing that we cannot have it all, in the sense that K plus D is bounded by n plus 1, and this is what is said by the singleton bound. So basically what you want is to construct code and have a trade-off between the redundancy you are going to add and your capacity of error correction. And so where AG codes enter the game, and where the algebraic geometry has to do with this codes? Well, one of the main example of linear codes are the Ritz-Solomon codes that are constructed by evaluating univariate polynomial of bounded degree at some points in a finite field FQ. So those codes are known to be optimal codes in the sense that their parameters reach the singleton bounds, k plus d is equal to n plus 1. But the point is that since you use the elements of FQ to construct these codes, you cannot construct codes longer than Q, which means that if you want very long codes, you will be forced to use finite fields of very large cardinality. And from a computational point of view, this can be hard. And this is exactly one of the motivation behind the use of curves in the construction of these codes. Indeed, AG codes are nothing but a generalization of Ritz-Solomon's code, where instead of considering polynomial, we are going to considering rational function in the Riemann-Roch space of curves, and instead of considering the element of FQ, we are going to considering points on a curve. So here is the picture, and those codes also have a lot of application, and some recent ones are in the clouds, where we use locally recoverable codes, and also in the IOP, which is some blockchain technologies. And so, of course, in order to construct these codes, to use them, we need to make an explicit computation of these spaces of function that I will call L of D, which are called Riemann-Roch spaces. And so let me just give you an idea of what it is a Riemann-Roch space, which is an object which is quite easy to present. So, and I will talk about Riemann-Roch spaces on curve in particular. So the divisor on a curve is a sum of points with some coefficients n of p, and the Riemann-Roch space associated to D is the space of all rational functions, so quotient of polynomial g and h, such that every point p that appear with a negative coefficient must be at 0 of the function, so at 0 of g. Every point p that appear in D with a positive coefficient then can be at 0 of h, so a pole of the function, but the function cannot have other poles outside this point that I just mentioned. And so we know by the Riemann-Roch theorem that those spaces have finite dimension, but we cannot have, by this theorem, a method to compute a basis of these spaces. So this was exactly the focus of one of my last work. And indeed, the problem of computing this space has taken mathematicians for a long time. In general, we split in two different methods of the state of the art. I will be focusing mainly on the first one, so geometric methods that come from the theory of Brill Noether developed in 1874. And in particular, in these last 3 years, we had some papers that use this theory in order to propose algorithm that can compute L of D for nodal curves and ordinary curves, where these two adjectives attached to curve simply tell you what kind of singularity, so singular points you can have on the curve. And what we're missing till now was an algorithm that work also for the general case of none of the curves we have non-ordinary singular points. So this was exactly the focus of the project that we did last year, and which relies on Brill and Noether method that give you necessary and sufficient condition on H and G such that G over H is in L of D. So basically you are given a curve and a divisor D on the curve, and this method gives you a description of L of D. So it gives you all the condition on G and H. So in particular, the elements of L of D are of the form Gi over H. So in particular, you can see that you can have a common denominator for the function of L of D. And H must pass through all the singular points of the curve, and the divisors of H must be bigger than D. While for what concerns the Gi, they must have the same degree of H, be coprime with the function defining the curve, and their divisors must be bigger than the divisor of H minus D. And so one can ask, for instance, how we can deal with the singular points on the curve, so about the second condition on H, and this can be rephrased using a particular divisor, which is called the adjunction divisor A. And so one can rephrase this condition on H by saying that you want the divisors of H to be bigger than A. And so all the condition that we have on the Gi and on H depends all on divisor. And so we also need to handle divisors, and we do this by representing them as multiset. And this allows us to have a routine on divisor, like summing them with a cost which is negligible. And so as you can imagine, the algorithm goes as follows. So you want to compute A, then you compute a common denominator H, and then you compute the numerators Gi. So you have a basis of L of D in terms of the Gi and H, but I just want to give you an overview or what is behind all this computation. So the computation of A can be done using representation in terms of the Puiseux expansion around the singular point of the curve, for which we have some algorithm that has been developed this year. And the condition on H and on the Gi can be translated in a linear system, then can be solved with the classical Gauss method, or you can rephrase them with a structure of Kx module, and then use algorithm from structural linear algebra, which are in general faster than the classical one. And so what we get at the end is an algorithm that is able to compute a basis for L of D, so for the Riemann-Roch space of any type of curves, which allows them now to construct AG codes from any type of curves. And so I will just end my talk by telling you what happen if you want to pass from curves to surfaces. And the main difference here is that divisors now are no longer sum of points, but sum of curves. But Riemann-Roch spaces are again spaces of function, and so you can construct AG codes exactly as in the case of curves. But why should we be interested in these codes? Well, first of all, because of the number of points on surfaces that in general have more points than curves, and this allows you again to construct longer code on a quite small finite fields, which is more convenient from a computational point of view. Then these codes turns out also to be interesting in some cases. For instance, they provided optimal local recoverable codes, and they are also of some mathematical interest. And what we can say about these codes, because the main point here is that we know less about surfaces, and we are not capable, for instance, to compute Riemann-Roch spaces in every case for surfaces, as is now it's true for the curves. So what we can say, of course, is that the length of those codes equals or is bounded at least by the number of rational points on the surface. We can say something about the dimension of the codes, because we can use the version of Riemann-Roch theorem for surfaces and then bound the dimension of these codes. But we can also say something about the minimum distance, which is one of the main parameter of the codes that I told you about at the beginning of this talk, because in particular we can show that D is bigger than the length minus this quantity, which depends on the number of rational points on some curves that are on the surface. And here is exactly where we can use tools from algebraic geometry in order to study these codes. And why this is important? This is important because the bound that you can get on D depend on the invariant of the surface. And this will then give an hint on which surfaces will give potentially better codes. So just to give you an idea of what are the types of bound that one can get, I will show you just two examples, but very quickly. So for instance, in the case of billion surfaces, we show that considering codes from surfaces that do not contain curve of small genus could be interesting. And in the case of codes from fibered surfaces on a base curve, we show that if you can choose B to have a few rational points, so the base curve, this will potentially give better codes. And so what it is left to do for what's next, in the case of curves, we are going to implement the algorithm for the computation of Riemann-Roch space of curves, and we will extend our work to the case of finite fields of small positive characteristics, because what we have done since till now is on field of larger characteristics. And for what concern AG codes in higher dimension, one interesting thing to do will be to study codes from threefold. So see how we can use tools from algebraic geometry to this course and computing Riemann-Roch spaces of surfaces. And I stop here and I thank you for your attention. Thank you very much.